Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. This is a series of lectures on computer architecture. So, we have been looking at input-output systems and we looked at how data transfer is carried out with the help of interrupts. We talked about handling interrupt service routines and we were looking at the issues of handling multiple interrupts. So, we will continue on handling multiple interrupts and in terms of priorities and so on, and we will also look at direct memory access, which is DMA transfers. So, let us look at this problem of handling many interrupts. Now, the questions we need to handle when we talk about handling many interrupts are the following. The first is, how does the processor know which device has generated an interrupt? Second is, how does the processor know which interrupt service routine needs to be executed? Third is, when the process is executing an interrupt service routine for one device, can another device interrupt the processor? And the fourth is, if two interrupt requests are received simultaneously, then how to break the tie? So, we have already looked at handling the first 2-3 questions, which is handling which is the identification of the interrupt by means of a vector and so on. So, we have also looked at handling priorities, but with respect to handling priorities, that is handling when we have multiple interrupts, determining whether one device gets higher priority than another device. So, that is an aspect that needs to be understood very well, because we when we have multiple devices which have to interrupt, which need the service of the processor, it is very important that certain devices are not starved for service. So, we need to understand how the priorities have to be handled. So, we will take a look at priorities in detail now. The priority level for a processor can normally be assigned under program control. So, what we normally do for this is that the priority, we say that the priority level of a processor is the priority of the program that is currently being executed. So, when the process starts executing the interrupt service routine of a device, its priority is raised to that of the device. So, every device is given a priority and the processor's priority is raised to the priority of the device that is now given the interrupt, that is the ones which interrupt service routine is being executed. So, when the process starts executing the ISR of a device, its priority is raised to that of the device. So, the device sending an interrupt request has a higher priority than the processor, that is the one which is currently being executed. Then the processor accepts the interrupt request. So, this is the basic mechanism that we use in handling priorities. So, if I have a device coming in which has a higher priority than the priority of the process that is currently under execution, it will be accepted. Okay, that interrupt service routine will be accepted. The process priority, as we already mentioned, is encoded in a few bits of the processor status register. Now, every processor will normally have a process status word or a process status register, and current priority is a field which is there in this process status register. Okay. So, priority can be changed by instructions that write into the process status register. Normally, such instructions are privileged instructions, okay, which can be executed only in the supervisor mode. So, privileged instructions cannot be executed in the user mode, and if a user program tries to accidentally or intentionally change the priority of the processor, that normally will raise an exception, okay, and that will be trapped. Okay, so, that is something that we do. So, by using this priority information which is there in the processor and the priority that is assigned to each device, you are able to handle the priority, you are able to determine which device can be allowed to interrupt and which device cannot be allowed to interrupt. Okay. So, when we are handling these priorities, let us look at how these different priorities are actually known to the processor. Okay. So, what is normally done for this is that when we have multiple priorities, it is often found that we can have different devices having separate interrupt request and interrupt acknowledge lines. Now, remember we talked about interrupt request line and interrupt acknowledge line as special control signals which are there on the bus. Okay. Now, it could have been a situation where we only had a single interrupt request line which was shared by different devices. When we need to assign priorities to different devices, what is normally done is that each device is given a separate interrupt request line and a separate interrupt acknowledge line. So, that is what you can see in this picture here. So, if you see here we have devices 1, 2 all the way up to P. So, each device has its interrupt request line, the INTR line going from device 1. Similarly, you have an INTR 2 going from device 2 and so on. And there is an interrupt acknowledge line which comes from the processor individually to each of the devices. So, all these interrupt request lines go to what is called as a priority arbitration logic, which is there inside the processor. So, this arbitration logic will determine which is the higher priority device, because it knows that different interrupts coming from different devices. So, this can assign different priorities to these different devices. So, the handling of the priorities will be done by this priority arbitration logic. All the arbitration logic needs to know is which device is the one which is currently raising an interrupt, and that is known by having these separate lines for each of these interrupts. And similarly, we have separate acknowledgement lines for each of the devices, so that the processor can tell that particular device that its interrupt is being processed. And as I said, each interrupt request line is assigned a different priority level. But so by means of this priority levels which are assigned to these interrupt request lines, you can specify which device needs to get a higher priority. Okay. So, and as I said, the priority arbitration circuit is the one which will take care of resolving all the priorities. So, when the interrupt request has a priority level which is higher than the priority of the processor, then the request will be accepted. The next question that we were looking at is what happens when you have simultaneous interrupts, that is, which interrupt request does the processor accept if it receives interrupt requests from 2 or more devices simultaneously. Okay. So, look at this situation for instance. Now, we said that there are different interrupt requests coming in from different devices. What happens if 2 interrupts come in simultaneously? Okay. One answer is very simple. If we already have a priority structure, right, if the devices are organized in a priority structure, then the processor accepts the interrupt request from a device with higher priority. Right. This answer is very obvious because we have 2 different devices and already we have a priority structure between them. So, there is a priority structure available, then depending on which one has a higher priority, that one's interrupt will be processed first. Okay. So, this is a very simple thing to do. But if we do not have such different priorities, then we need to look at a different mechanism. In this case, that is when we have the priority structure in place, since each device has its own interrupt request and interrupt acknowledge line and a different priority level is assigned to the interrupt request of each device, it is very easy to disambiguate between these different interrupts. So, what happens when this is not the case and you have devices sharing an interrupt request line? Okay. So, when they are sharing an interrupt request line, then how can the processor decide which interrupt request to accept? Again, if you think about it a little bit, the answer here is also simple. The one simple answer is that we again go in for a polling scheme because the different devices are sharing a single interrupt request line. So, what does the processor have to do now? The processor will have to go and poll the status registers of the IO devices to determine which device is requesting an interrupt. So, in this case, the priority will be determined by the order in which the devices are polled. So, if you have 4 devices which are connected to the same interrupt line, and if the processor polls it in the order of 1, 2, 3, 4, then obviously one gets a higher priority because if one has raised an interrupt, that will be recognized first. So, that is the order. So, the order in which the devices are polled will determine the priority of the devices. Okay. So, that is what happens in a polling scheme. When the device is polled, basically you will check its status bit. So, the first device which status bit set to 1 is the device whose interrupt request will be accepted. So, once that is serviced, then the next device can be serviced and so on. Right. So, this is a mechanism that is typically used. So, when we have this sharing of a single interrupt request line by different devices, we use what is called as a daisy chaining technique or a daisy chaining of interrupts that is normally used. So, you can see what happens here. When you have a daisy chaining mechanism that is used, you can see that the different devices here, device 1, 2, etc. n, are all connected to a single interrupt request line which goes to the processor. And similarly, there is a single interrupt acknowledgement line. Okay. Now, this interrupt acknowledgement line is the one that is kind of daisy chained. So, what we mean by a daisy chain is that the interrupt acknowledgement line comes as the input to device 1 and then from the device 1 it goes to device 2, then from device 2 to the next device and so on. The way the whole thing will work is like this. So, when a device raises an interrupt request, the interrupt request line will be activated and it will go as an interrupt to the processor. Now, the processor now in turn will generate an interrupt acknowledgement signal. Okay. So, when the processor generates the response, which is the interrupt acknowledge signal, it is first received by the device 1. Okay. So, if device 1 does not need the service, then it will pass it on to device 2. Again, similarly, if device 2 does not require the service, then it passes it on to the next device and so on. So you can see that because of the order in which the interrupt acknowledgement is processed by the devices, okay, the device which is electrically closest to the processor has the highest priority. That is, this device which is closest to the processor will be the one which gets the highest priority. So in this case, you can see that this is different from the polling mechanism we talked about earlier. In polling, what would happen is that the processor will go and check the status register that is there in each of the devices, and that will determine, and depending on which one it polls first, that gets a higher priority. Now here we are talking about a slightly different mechanism where electrically the way the devices are connected is different, that is, the way the interrupt acknowledgements are connected to the different devices is different, and the order in which the interrupt acknowledgements are connected, that determines the priority of the different devices. Okay. So this is what is called as daisy chaining of interrupts. So you looked at two techniques here, one is a polling mode and the other is daisy chaining of interrupts to determine which device gets a higher priority. We also looked at the priorities technique. So we actually have three techniques: priority based determining of which device gets which device gets a higher priority, that is explicit priority given. The second is the polling based technique. Third is the daisy chaining technique. Now we can also have combinations of these techniques in order to organize the different priority structures. Okay, one such organization is the combination of priority mechanism and the daisy chaining. Okay, so what we do here is, so you have these different interrupt lines as we have, so interrupt 1, interrupt 2, interrupt P and so on. So these interrupt lines are shared by multiple devices. So which means I have device here, a device here, both these devices are sharing an interrupt 1 line. Similarly, I have another device and a device here, these two devices are sharing this interrupt line. Okay. So we have, for instance, interrupt 1, interrupt P, let us say, two different or P different lines that we have here, interrupt lines. So if you do not allow this sharing, you can only have P different devices which are given different interrupts. Now we are talking about sharing of a given interrupt line itself by multiple devices. So what happens here is, now between these devices, you have a daisy chaining of the interrupt acknowledgement signal, so that when this interrupt is given to the processor and the processor responds with an interrupt acknowledgement signal, that interrupt acknowledgement signal first is given to this device. So if this device has raised the interrupt, then it will use the service of the processor. Otherwise, this device will pass on the interrupt acknowledgement to the next device. So in the order in which these devices are connected will determine which device is the one that is going to be serviced first. Okay. So you can say that you have different groups of devices, okay, which are sharing a particular interrupt. So you will group them such that all of them belong to a particular priority. So you may have various devices that are there. So you kind of group the devices in terms of, okay, these devices are priority 1, these devices are priority 2 and so on. So the ones which are priority 1 will be sharing an interrupt line. The ones which are priority 2 will share another interrupt line and so on. Okay. So this is a scheme in which you can have different devices sharing the available interrupt resources. Okay. This is a combination of various schemes. We will take a short break now and then come back and continue with the details of other interrupt related mechanisms. Welcome back after the break. So we looked at how the available interrupt resources can be shared by different devices by using a combination of daisy chaining and priorities and polling and so on. Okay. There is another important aspect with respect to enabling and disabling of interrupts, which also we need to pay a little more attention to. Now we have already talked about enabling of interrupts and disabling of interrupts. So what we normally do when we talk about enabling interrupts is that only those devices that are currently being used in a program should be allowed to generate interrupt requests. Now this is a requirement that we may have for certain programs. Okay. So in this case, what we do is to control which devices are allowed to generate interrupt requests, the interface circuit of each IO device has an interrupt enable bit. So if the interrupt enable bit in the device interface is set to 1, then the device is allowed to generate an interrupt request. Okay. So we are talking now about having an interrupt enable bit in each IO device. Okay. Only if this interrupt enable bit is set to 1, that particular device itself is allowed to generate an interrupt request. Okay. So this is a mechanism by which you can control whether a particular device is allowed to generate an interrupt or not. Now we already talked about an interrupt enable bit which is available in the processor side, okay, which determines whether the processor is going to service other interrupts which are coming from other devices or not. Okay. So, we are now talking about two different interrupt enabled signals, one on the device's interface circuit, which determines whether the device is allowed to generate an interrupt request. Another is the interrupt enabled bit, which is there in the process status register or the priority structure of the interrupts, which determines whether a given interrupt will be accepted or not. Okay. So, therefore, when we talk about enabling interrupts, we need to be sure about which enable we are talking about, whether we are talking about the device's interface circuit, the enable bit which is there in the device's interface circuit, or the one which is there on the process status register. Now, it is a combination of these two that controls which device is allowed to generate an interrupt and which device's interrupt will be serviced. Okay. This is something that we need to keep in mind. So, now when we talk of interrupts, now remember that this handling of interrupts is very similar to the idea of exceptions that we have referred to much earlier. Okay. So, in general, the term exception is used to refer to any event that can cause an interruption. So, we can say therefore that interrupt request from IO devices is one type of an exception. Okay. Now, other types of exceptions are recovery from errors, debugging, privileged exception and so on. Okay. So, what is the difference therefore between handling IO related interrupt request and handling of exceptions due to other errors, okay, or other special conditions? Okay. This is one small aspect that we need to pay attention to again. So, in the case of IO interrupt request, the processor usually completes the execution of the instruction which is in progress before branching to the interrupt service routine. Okay. That is, we said that an instruction I would be in execution. So, that instruction will be completed and then you will move to the interrupt service routine, come back and resume from instruction I plus 1. So, this is what we looked at. Okay. This is what normally happens when we are looking at IO related interrupt requests. But in the case of exception processing, the execution of the instruction in progress usually cannot be completed, because the exception may be because of something which is preventing that particular instruction itself from being executed. For instance, if you have a cache miss exception, so that is an instruction is being executed, it requires a memory data from memory, but that access for instance cannot be completed, a cache miss or a page miss can happen. So, when that happens, an exception will be generated, and when that happens, that instruction itself cannot be completed. So, the instruction will be stopped in the middle, right? Not, so you do not handle that exception after that instruction is completed, but you handle it as soon as it occurs. Okay, this is one very important difference that we normally need to keep in mind between handling of interrupt requests which are generated because of an IO operation and because of other such exceptions that can happen during the course of a program execution. Okay. So, this is with respect to various aspects of the of handling interrupts in general. Now, we can see that compared to the polling scenario, the interrupt service routine based transfer is a faster mode of transfer. But we will see that even in this case, even when we have an interrupt based mode of data transfer, the overhead in handling this interrupt service routine, that is saving all these registers and then going and executing the interrupt service routine, some instructions that need to be executed for doing the data transfer, that itself has a higher overhead. Okay. So, let's take a look at how much overhead that how overhead is caused by this kind of an interrupt service routine. Okay. So, let me take this example here, right. So, we are looking at some instruction here, add, subtract, and, or, knobs is the user programs instruction that you have. Now, let us say I have an IO interrupt that occurs in between this and or, for instance. So, what do we need to do here? You need to save the PC and then move to the interrupt service address. Okay, let us say this is the interrupt service address that we have here. Okay. So, you will move to this through this and then you will execute this interrupt service routine. Now, let us say this interrupt service routine is for some IO transfer, which means you will read some data, store it in some memory, that is you will read the data from the IO device, store it in memory, okay, and then do whatever is required, and then you will return from the interrupt service routine, what is called as an RTI instruction. So, when you return from the interrupt service routine, you will come back and resume over here. So, when you are resuming over here, you will again bring back the contents of the PC and then you will start your execution from here. Okay. So, this saving PC, executing this interrupt service routine and coming back to the restoring the PC. This job will have to be done for every data that needs to be transferred, or every set of data that needs to be transferred from the IO device. Okay. So, let us look at the time that it takes for doing this. Let us say for instance, we are looking at doing 1000 transfers at 1 millisecond each. Okay. So, we are looking now at 1000 interrupts, let us say, that are going to be generated at 2 microseconds per interrupt. Okay. So, that is for every data transfer that needs to be done, an interrupt is going to be generated. So, 1000 interrupts at 2 microseconds per interrupt, and if 1000 interrupt services at 98 microseconds each, let us say, that is for every interrupt that is generated, 98 microseconds are required for interrupt service, let us say. Okay. So, this will give you almost 98 plus 2, that is about 100 microseconds for 1000 interrupts. So, it will give you about 0.1 CPU seconds, let us say. Okay. Let us look at the time taken for the data transfer as such. Now, if you had a data transfer rate of 10 megabytes per second, assuming that we could do a 10 megabyte per second data transfer, we want to know how much time it would have actually taken for transferring 1000 bytes. Let us look at this. So, 10 megabytes per second would mean that I can transfer 1 byte in 0.1 microseconds. Okay, 10 megabytes per second would mean that 1 byte can be transferred in 0.1 to 10 power minus 6, which is 0.1 microseconds per byte. 0.1 microsecond per byte, what will be the transfer time for 1000 bytes? That will be 100 microseconds, right. So, 100 microseconds for 1000 bytes. So, if I am doing 1000 transfers, okay, so 1000 transfers into 100 microseconds, that will give me 100 milliseconds, which is about 0.1 CPU seconds. So, what we actually see is that compared to the data transfer time that you have, the interrupt service routine time, the overhead of the interrupt service routine, okay, can be almost equal to that. That is, if I take 0.1 CPU seconds to the actual data transfer, okay, to actually move it from the device to memory, execution of the interrupt service routine also takes up so much amount of time. So, which means the overhead that I have for executing the interrupt service routine can be very high. Okay. So, which means we need better mechanisms, especially when you have large data transfers being carried out between the IO device and memory. So, we need to see whether we can get better mechanisms and faster mechanisms of doing this data transfer. That is, can we avoid this overhead that we have because of the interrupt service routine, wherein we are always under the control of the processor, and the processor has to go and do this data transfer, right. The processor has to go and read from the device and store it in memory. Can we do this independent of the processor? Okay, that is the next question that we ask. So, this idea of doing transfer directly, okay, is called as direct memory access. The need for DMA basically comes because, as I said just now, both in the case of polling and interrupt driven input output data transfer, it is a CPU which is responsible for doing the data transfers between the memory and the IO data registers, which can be very time consuming for high speed devices. Okay. So, we are now looking at something called a direct memory access. Now, in this direct memory access, what we will do is that we allow the OS, okay, to just provide the starting address where the transfer needs to be done, and have the IO controller, that is the device itself or a controller which is associated with the device, to do the transfer to or from memory autonomously. And once it has done the data transfer, it can interrupt the processor and let the processor know that it has completed the data transfer. Okay, this is called as the direct memory access. So, now we need a separate controller called a direct memory access controller or a DMA controller, which will handle these transfers independently. Okay. So, what we are talking about here when we talk about direct memory access, therefore, is we do not have to go to the processor and execute a program on the processor to do this data transfer. Instead, the DMA controller will directly transfer data from the IO device to memory. Okay. Okay. So, for instance, let us take a look at this picture here. The scenario we are talking about here is something like this. So, I have the processor, you have the main memory, and then we have these different IO devices. Now, I am saying that these IO devices are connected through a DMA controller to the system bus. Okay. Now, in the absence of the DMA controller, this is the situation we had was that a program on the processor is responsible for reading from the disk and storing it into main memory. Okay. Now, what we are saying is that this DMA controller which is available here will be the one that will take care of transferring data directly from the disk to the main memory, right, or from the main memory to the disk. That is, it does not require the interference or does not require the services of the processor. So, which means that when this is taking place, right, the processor can be free to do other work. Okay. So, that is, you do not disturb the processor for doing the actual data transfer. Only thing we need to know is we need to have the processor give instructions to the DMA controller to say where exactly in memory this transfer needs to be done. Okay. So, which is why we said that it is typically done by the operating system or a set of programs under the control of the operating system that will determine where we need to do the data transfer. So, this is what we mean by the DMA mechanism. So, let us look at the details of this DMA mechanism as such. What we have is, we have a special control unit which is provided to transfer a block of data directly between an IO device and the main memory without continuous intervention by the processor. So, this control unit is called as the DMA controller. Okay. So, what is it the DMA controller will do? It will perform whatever functions will be normally carried out by the processor. That is, for each word, it will provide the memory address and all the control signals. To transfer a block of data, it increments the memory addresses and keeps track of the number of transfers. Okay. That is, if you look at this picture here, this DMA controller is the one that will keep track of using the system bus in order to do the data transfer to the main memory. So, now the DMA controller can transfer a block of data from an external device to the processor without any intervention from the processor. But as I said, the operation of the DMA controller must be under the control of a program which is executed by the processor. That is, the processor must initiate the DMA transfer. Okay, so, the initiation of the DMA transfer will be done by the processor. So, how does the processor initiate the DMA transfer? It will do that by giving following information to the DMA controller. That is, the processor informs the DMA controller of the starting address, number of words in the block, that is the number of words to be transferred, and the direction of transfer. What we mean by direction of transfer? Whether it is be transferred from the IO device to memory or from memory to the IO device. So, these three things are specified by the processor to the DMA controller, and once it gets this information, it can directly do the DMA transfer. Once it does the DMA transfer, it informs the processor by raising an interrupt signal. So, that will be a signal which goes to the processor which says that the DMA operation has been completed. Okay. So, this is what is done. Let us summarize what we have been looking at in today's class. So, we have looked at handling of priorities and interrupts. So, we looked at how the interrupt lines can be shared, combination of daisy chaining and so on, and we looked at difference from handling, how interrupt handling is different from handling other exceptions, and we also looked at the overhead of ISR, that is interrupt service routine, when you have a data transfer. So, from that context we looked at the need for a direct memory access, and we also looked at how DMA basically works. So, questions to review contents of today. Question number 1, how is priority assigned to different devices? Question number 2, how does the interrupt mechanism work when the devices are daisy chained? Question number 3, how does handling of interrupts differ from handling of other exceptions? Question number 4, why do we go for DMA? Question number 5, what is the information required for a DMA transfer? Thank you.